Hi class, we are now on 16.5. This is Equilibria-Reactions involving solids and liquids. I've actually already covered this, so this should be pretty easy to understand. There's not really much to it. It's just to reinforce how easy it could be to make mistakes on certain problems if you're not paying attention to what the phases are. So equilibria that includes species in different phases, that is called heterogeneous equilibria. That's the same term of heterogeneous mixture compared to homogeneous mixture. If you think back to 110, if you took 110 at citrus. So equilibrium constant expressions do not include any solids or liquids. I've already said this. Why? It's because only aqueous and gaseous species have concentrations that can change. Solids and pure liquids, we do not count them. So if we look at this, the concentrations of pure solids and pure liquids do not change during the course of a reaction. Because they do not change, they cannot be included in the equilibrium constant. So if we look at this reaction here, gas, liquid, aqueous. So we have 4 species in this reaction, but we're only going to have 3 because we're not going to include water in this, and it shouldn't be included or it would be wrong. So we have our products on top and we have our reactant on the bottom. So why do we not include something like solids? Well, we see this reaction here, and carbon is part of the product. Now, if we add 2 different amounts of carbon in this and allow the reactions to go, what we'll notice is that the reaction will go on its own, so they'll have the same concentration of CO2 and the same concentration of CO at equilibrium in these 2 separate reactions, even though there's different amount of carbon, which means that the carbon has nothing to do with the reaction itself. So it does not count to be in the equilibrium because it's not playing a part in it. Okay, so here's a question. For which reaction does the equilibrium constant of partial pressure equal the equilibrium constant of concentration? So remember, if for Kp and to equal Kc, the sum of the products has to equal the sum of the reactants. So I'm just going to go through these. We have 2 and 2, that's 4, and 2 and 3. So this doesn't equal. We have 1 and 3, that's 4, and 2 and 3, that's 5. And we have 1 and we have 3. So something's wrong here. I didn't do something right. And for those of you who probably already caught it, great. We have solids. We have solids in this. So if you just jump right in and do a problem, and you don't catch that you're doing something wrong, your answers are going to be wrong. So now we do not count solids or liquids. So let's go back and count what actually counts to an equilibrium constant, and we can see which one. So we're not going to count the solids. So there's 1 and 1 on this side. Oh, sorry, 2 and 1. So it doesn't equal. We have 3 and we have 3. So this one does equal. So this is most likely our answer. And we have 0 and 3. So this one, so B is going to be our answer because we have 3 moles on this side and 3 moles on this side, and we are not paying attention to the solids at this case. So this is where it would also make sense of, remember the Kp? So if this is the same number, that's where Kp is going to be equal to each other. 3 minus 3 is 0. That's going to knock this out and leave it with Kc equals Kp. Oops, I think I went too far. All right, so now let's write equilibrium constant expressions for both of these. Pay attention. First things you should do, look at the state, the physical states, before you even do anything else, because that will catch you. You will catch yourself making a mistake. So here we have a solid. So we're only going to have an equilibrium constant with products. And over here, we're going to have 1 and 1. We have 3 species here in this balanced equation, but we're not going to count the water because it's pure liquid. So if we write these out, we do not include the reactant, and here we do not include the water. And that's it.